Over the course of my studies in theoretical physics, I've traveled across the continent and around the world sampling new ideas and tasting different answers to the questions of how and of why. And still, I find there remains a deep hunger which lives within me, a burning desire to share these great ideas with the people around me. And so, I have assembled a team of some of the greatest, most lucid, most creative minds I've encountered in my travels. And I call them my Titanium Physicists. You're listening to the Titanium Physicist Podcast, and I'm Ben Tippett. And now, allez, physique! So, Titan is cool. It's Saturn's largest moon. It's 97 Kelvin. That's about minus 200 degrees Celsius. It's essentially a big ball of ice floating around a giant planet in the middle of the solar system. But it's got lakes of liquid hydrocarbon, and it's got an atmosphere, and it's got dried riverbeds, and it's got dunes and lakes and robots. And hey, you know what else has these things? Earth. And you know what else has these things? Mars. So today we're going to explore how such dissimilar planetary bodies can have such similar features. Okay, today my guest is Mr. Ryan North. He's a professional webcomic artist, writer, and Duke of the Internet. He writes dinosaur comics at quants.com. Hello, Master North. Welcome back to the show.
Thank you very much for having me back.
This is Ryan's second appearance, and he's got a newish book out, Dinosaur Comics, Everybody Knows Failure is Just Success Rounded Down. He also just wrote the Adventure Time comic book. How'd that go?
Good. I mean, the first issue comes out in February, so we'll see then if I manage to do a good job.
Fantastic. So, Ryan, because your comics and writing are out of this world, I have assembled today a panel of two of my favorite planetary titanium physicists. Arise, Dr. Catherine Neish.
I have arisen.
Fantastic. Dr. Catherine did her undergraduate at UBC with me and her PhD at the University of Arizona in planetary science. She's currently at the Johns Hopkins University Applied Physics Laboratory. And now, arise, Dr. Charlie Barnhart.
Hello, world.
Dr. Charlie did his undergraduate at the University of Washington in Seattle in physics and astronomy and his PhD at the University of Santa Cruz. He's currently a postdoc at Stanford working for the Global Climate and Energy Project. Charlie's also on the hit science podcast Science Sort Of with me.
You're here.
Awesome, Charlie. So today's topic is Titan and Mars and why they look like Earth. So let's start talking about Titan because nobody talks about Titan enough.
Titan is one of the most interesting places in the solar system. And I would argue that it is the most Earth-like planet in the solar system, other than Earth itself, of course. Titan is the largest satellite of Saturn. Actually, it's the second largest moon in the solar system. It's bigger than Mercury. If it didn't happen to orbit Saturn, it would probably be called a planet on its own right. It has a huge atmosphere. It's the only moon with a substantial atmosphere. Its atmosphere is actually larger than the Earth's. With 50% higher pressure at its surface than we have on the Earth. And what makes it like the Earth? Well, it's got this large atmosphere made of nitrogen, just like the Earth does. It has lakes filled with liquid. It has streams and sand dunes and mountains and volcanoes, maybe. All these things that we see on Earth. But it's like a bizarro Earth, whereas instead of having rock made of silicates, the rock is ice. It appears to be a large ice ball. And instead of having water flowing over the surface, it's liquid methane and liquid ethane. So oil. Oil is flowing over ice and making all these features that we see on the Earth. So we really didn't know a whole ton about Titan until actually pretty recently. We'd never seen the surface of Titan until 2004. That was only 7 years ago when the Cassini orbiter arrived at Saturn and started taking pictures And what Cassini had that no other spacecraft had before is a radar. And so what this can do is it can peer through Titan's big hazy atmosphere to see the surface, which had never been seen before, because Titan actually has a whole bunch of organic gunk in its atmosphere. Along with that nitrogen is methane. And that methane reacts with sunlight and with other charged particles to create this gunk that sits in the atmosphere, obscuring the surface, and eventually rains down onto the surface to make the streams and the lakes that I was telling you about earlier. In addition to Cassini, which is still orbiting Saturn, knock on wood, it's doing quite well, there was also a robot that landed on Titan in 2005 called Huygens, after the guy who discovered Titan so many years ago. And Huygens is the farthest planetary probe that humans have ever placed on another object. And it descended through Titan's atmosphere, took a bunch of readings, and then eventually landed and stayed on the surface of Titan for several hours before it eventually froze to death. But we learned a lot about Titan from those few hours that we're still analyzing today. We're hoping to send another spacecraft to Titan. It's called the Titan Mare Explorer. It's currently in the running for NASA's next Discovery mission. And the idea of this mission would be to send a boat to Titan. It's the first extraterrestrial boat, which would land in one of Titan's polar lakes and take measurements of the lake composition, how deep the lakes are, what the weather's like on Titan, whether we should build our next beach resort there. So that's Titan in a nutshell.
Can I ask some questions?
Yeah, please. I was hoping somebody would break in there.
Okay, so this is going to make me sound really dumb, but you said there was oil on the surface, but I was under the impression that oil came from dinosaurs.
Yeah, it's a different type of oil. It's, I guess, a more pure form of oil. It's made of methane and ethane. So methane is carbon with 4 hydrogens, and ethane is 2 carbons with 6 hydrogens. And we think that Titan just formed with these elements. And when it formed 4.5 billion years ago, it condensed with these molecules that at Earth are really, really volatile. They'll evaporate really quickly.
Right.
And so, but since it's so cold out at Saturn that you could condense with these more volatile elements.
Right. So but there's been the 2 spacecraft that have gone around or visited this moon. Only 2, right?
Oh, well, there were the Voyager spacecraft.
Yeah, but they just sort of whizzed by and said hi.
Yes, they did whiz by.
So isn't it possible that the oil could be from dinosaurs, and we don't have any evidence for that yet?
It's true that we don't know that there weren't dinosaurs on Titan.
And you say you have a PhD.
It's one of those unknowables, right? Whether or not there were dinosaurs on Titan is not really a testable hypothesis, and I would argue is not science. Okay.
It's testable. I mean, I don't want to go around saying, like, putting a quote to your name that says the oil on Titan came from dinosaurs, but it sounds like that's what you're saying. At least it's possible.
Sure. Anything's possible, right? The thing about science is you have to find a way to test that. So.
Right. Well, I mean, I was listening to our introductions, and it was like, here are these great people who have accomplished so much in their life and have all these degrees, and here's Ryan who's written some comics. And so what I'm trying to do is ruin these 2 careers by dragging you down to my level and making you seriously argue that there were dinosaurs on or not on Titan.
People do argue that there is life on Titan. It would have to be a very different life than the life we have on Earth.
Life, but not as we know it?
But not as we know it, yeah. And so one of the things that this new spacecraft is interested in looking for are strange... The boat, yeah. Are strange organic molecules we can't explain by inorganic processes alone.
Right. That'd be amazing.
Yeah, it'd be really hard to detect. Detecting life in the solar system, even if it exists, is going to be really hard to do because we're really good at looking for things that are like us, and we're really bad at looking for things that aren't like us. So if we do find something, it might just be us, you know? And if we don't find it, it doesn't mean it's not there. It just means we don't know how to look for it.
So this boat, you say a boat, and I worry this is like the dumbing it down language where it's not going to be a boat coming in on a parachute, but something that is analogous to a boat, but not actually, a motor out back.
I like to compare it to Huygens, which is the spacecraft that landed on Titan in 2005. But now we know where to put Huygens. We know where the lakes are now. When Huygens landed, we have no idea where it was landing. We thought Titan might be entirely covered in liquid, that there was a huge planet-wide ocean of ethane. We know now that's not the case. Now we know where the lakes are, and so now we know where to put the boat. If we were to do Huygens with the information we have now, we would put it in the lake. So it's like Huygens in a lake.
So we just got lucky that Huygens didn't hit the lake and sink.
Actually, it was designed to land in liquid.
Really?
So I guess it depends on what you think is luck. Maybe it was unlucky in that we didn't land in the lake.
Could it have done different things if it had been waterborne?
Well, the liquid is not water. It's hydrogen.
Well, yeah, I meant metaphorically waterborne.
Sure. Yeah, actually,
change your language for this, eh? Had it been ethane-borne?
Ethane-borne, yeah. It had a sonar on it that could have detected the lake bottom. So it had a couple of instruments on board that were meant to be submersed in water that just never got used because
Didn't it have an accelerometer so it could test wave periodicity and ascertain wind speeds, things of that nature?
The spacecraft has an accelerometer, and yeah, you can back out that information.
Did you just say that every spacecraft have an accelerometer?
Well, yeah, most of them do. Landers usually do.
That's awesome. I just love the, please, every spacecraft has an accelerometer.
Yeah, I was like, oh, shut up, man. Obviously.
A Wii remote has an accelerometer.
When you've landed, right? You want to know when you've hit the surface, so you need an accelerometer.
Obviously. All right, so I'm with you so far.
People like to call Titan, it's very Earth-like, but we were talking earlier, and Charlie was arguing that, that Mars was the most Earth-like planet in the solar system?
No, I said Earth is the most Mars-like.
Yeah, there you go.
Ooh, what do you mean by that?
Because Mars has many features that Earth has, but Earth has many features that Mars does not have. So it's the comparison from Earth to Mars is more direct than comparing Mars to Earth. What I'm trying to say is they're both silicate bodies with evidence of geomorphic activity, water-carved features, dry lake beds, mountains, volcanoes, all sorts of things in common. But then Earth has other things like cats and YouTube that Mars does not have.
Cats and YouTube being the two distinguishing features of the two planets.
Exactly.
So far, I'm more inclined to go with your side, Charlie, because Catherine's introduction was, talking about how the planets are similar, but using language in this really subtle way to be like, oh yeah, they both have lakes full of liquid.
Well, yeah, but
what's interesting
it's the
about
only place with liquid.
Is it the only place in the solar system with liquid?
Other than Earth, unless you count liquid hydrogen, and then Jupiter has that.
Some frozen ice found on the polars.
It's frozen.
Well,
it's
that's
frozen.
A form of liquid, the solid form.
And Mars may have liquid deep underground,
but not on the surface.
So I think a more precise way to say it is they have an active cycle in which a compound exhibits itself in 3 different phases: solid, liquid, and gas.
Although it might not actually be solid on Titan. It might not get cold enough for there to be solid methane or ethane right now. But it is close to the triple point.
Sure, it gets cold enough up in the atmosphere.
So does it snow methane?
So you're saying like higher up in the atmosphere if it's frozen out. Yeah, I'm not sure if that's where the methane precipitates, though. I think it's lower down in the atmosphere where it would be liquid.
So on Earth, it's interesting because we fill wine bottles up with hydrocarbons to make Molotov cocktails. On Titan, you would fill a bottle up with oxygen and then chuck it at the hydrocarbons.
Right. So actually, there was this really funny letter to Nature a while back. This guy was really, really concerned about sending Huygens to land on Titan because there's tons of acetylene there. And acetylene is very explosive on Earth. And he's like, if you land this spacecraft on Titan, the whole moon's going to blow up. Of course, that's not the case because plenty of things are impacting Titan all the time. And there's also no oxygen there. So
for the combustion reaction to occur, you need a hydrocarbon plus oxygen equals CO2 and water. And the plus oxygen was missing.
Totally missing. Yeah, there's very little oxygen on Titan except in the form of frozen water ice.
So if you have a canister full of oxygen on Titan, you've got a bomb if you just chuck it?
Exactly.
So if you had a base on Titan, there'd always be a danger of getting a leak and then a spark and the whole base explodes.
Well, that's why you add nitrogen, right?
Well, I mean, we'd want to learn that lesson the hard way.
I think we already did. It was called Apollo 1.
Oh, no.
Oh,
we did.
Sad face. Sorry, I just brought the mood down.
Yeah, now that we brought actual death into this, instead of just cartoon explosions, let's continue.
So, Catherine, why does Titan have... Why are there so many hydrocarbons there, as opposed to, here?
It probably has something to do with the fact of where Titan originated in the solar system. Out where things like methane can condense and are stable and are not going to evaporate or sublimate away like they do in the inner solar system. But why Titan in particular has a huge atmosphere with methane in it is sort of not well known. One idea is that the methane was trapped in the inside of Titan and it's slowly leaking out over time because Titan actually shouldn't have as much methane as it does. the methane in Titan's atmosphere gets destroyed on the timescale of about 10 million years. So either we're just ridiculously lucky and happen to see Titan after it burped a bunch of methane, or there's some process that's bringing methane out from the inside of Titan to the atmosphere. One of the early ideas for why Titan had so much methane in its atmosphere, or one way you could supply that methane would be from a huge ocean, that you had an ocean of ethane and methane, and the methane would just sort of evaporate from this ocean and supplement the atmosphere. But now we know that ocean doesn't exist, so that's why people are now looking for new ways to explain how methane can stay in the atmosphere without disappearing over time. Because when it reacts with the sunlight and with other particles in space, it turns into ethane and it turns into other heavier hydrocarbons that will turn into liquids and solids and fall onto the surface and just sit there. And since it loses the hydrogen to space, there's no way to go back once you've made these higher order hydrocarbons. Mm-hmm. So it's a current area of research, actually.
Well, just to clarify a small point, is it the current consensus that Titan sort of coalesced from the same accretion disk the rest of the planets came from?
Yeah.
Yes.
So why does it end up in orbit around this other planet instead of being a planet in its own right?
So I think the idea is that each of the giant planets had their own subnebula, it's called. So the sun had its own planetary nebula when it was forming. But one idea is that Jupiter and Saturn also had little nebulae, and that's where they formed their moons.
Yeah,
so it's a little mini solar system.
Solar systems. Mm-hmm.
Yeah, these nebulae were accreting from their own paths as they swept through the accretion disk of the solar system. And then there was an inner spiral where they were forming their own moons. Turtles all the way down.
Yeah, I didn't know that.
Okay, so let's bring it back to the overall topic, which is why the Earth and this weird moon around a gas giant and Mars all have similar features in their geomorphology. Yeah, why they have similar surface features. Okay, yeah, why? So what are they? The common ones talked about are dunes. So what's with the dunes on Titan?
Dunes on Titan are not the dunes you might have seen on Earth. So when I say sand dune, I mean something made out of micron-sized particles. Now, the composition of those particles can be anything you want. They could be made out of dinosaurs, for example. All that matters is their size. So on Titan, we have these sand-sized particles made out of presumably organic crud that fell out of the sky. Whereas on Earth, the sand-sized particles are made out of rocks that were churned up in oceans and rivers to make smaller particles. The important part is how big they are.
And their density.
So they can be picked up and formed into sand dunes. If they're too heavy, they won't get picked up. If they're too light, they won't induce other sand particles to hop and move forward to form these characteristic dune forms. So there's this sort of sweet spot that you want to get at in terms of size. And there's tons of them on Titan. They form this belt basically around the equator. There's more organic crud in these sand dunes on Titan than there is the coal reserves on Earth. So that's Titan. But on Mars, I guess they're more similar to the dunes we have on the Earth, except it's weird, right? Because the atmosphere is so much smaller.
Yeah, there's the idea that the particles are smaller as well, and the combination of higher wind speeds, reduced atmospheric viscosity, and lower gravity allow dunes to still form because there's a slightly different sweet spot. But clearly they do form because we see pictures of them. And Mars actually forms these really cool dunes called Barkin dunes, which are these curved shield-shaped dunes that actually self-replicate because the tails of the dunes create wind conditions that make other Barkin dunes behind them. What? There's great examples of them in the North Polar regions of Mars and I think in Colorado and various parts of South America. Does Titan form Barkin dunes?
No. The only thing we've really seen on Titan for sure are lots and lots of linear dunes, which are actually also relatively unusual on the Earth. And they're formed by wind that goes in two alternating directions. So if something's coming from the south and something's coming from the north, and they alternate, you'll get something going east-west. And that's what we see on Titan. Cool. And you also see them, for example, there's huge sand sea in Namibia on the Atlantic coast that looks very similar to the dunes we see on Titan.
What's interesting on Earth is the dunes are these very active features that change daily. If you watch dunes in the desert, you can just see them forming and rolling over each other. Where on Mars, we think they form really, really slowly. And some of these dunes might just be petrified relics of past climate regimes. Do you know if they're actively forming?
Again, not that we've seen. They might also be petrified relics. That would be a great discovery to see a moving dune on Titan, but we haven't seen that yet.
So what other geomorphological features are there? Okay, so rivers. Why are there rivers? Well, there are rivers on Earth because there's liquid water on Earth, right?
Yeah, so that's potential energy. If you have a mass of something higher than it could potentially fall, then it has gravitational potential energy, and it's going to move downhill unless something blocks it. Now, liquids occupy the shape of their container, so they're very good at moving downhill because they can zip around whatever things are blocking it. And when they start moving downhill, that gravitational potential energy turns into kinetic energy, and now it has momentum, and so it can push things, it can carve things, it can move sand on Earth and Mars or ice on Titan and begin to carve channels. And then once a channel is carved, subsequent water or liquids will naturally flow towards that channel, and the channel will carve deeper and deeper, and these begin to form networks. And so you get networks of channels, and when they get deep enough, they become streams, and deeper yet, they become rivers, and eventually they may hit a very big low-lying area and form a lake.
So are there rivers on Mars?
There were about 3.8, 3.6, 4 billion years ago, however you want to say it. There may have been several episodes of river formation in Mars's past. But yeah, there are huge, huge river networks, rivers that are as long as the Nile.
So what happened to the rivers?
Mars is a small planet, alas. So it has lower gravitational field. It has less of a thing called a geodynamo. So it has less radioactive elements because it's smaller. And so it can't keep a molten core, which allows a magnetic field, which prevents hydrodynamic escape and hydrogen loss from the top of the atmosphere. And the hydrogen loss leads to the separation of hydrogen from oxygen, which is water, and then the planet eventually dries up, and all the water is either lost or frozen.
So does Earth's magnetic field help to retain the water?
It does help. Two things help with Earth. It's higher gravitational field, so it's harder for things to escape from Earth. Its location in the solar system helps because water will not freeze out, because we live in a place where temperature equilibrium allows water to be liquid. And then, the magnetic field protects high energy gamma rays from entering the atmosphere and splitting hydrogen off of oxygen.
So Mars lost its water and atmosphere, you're saying about 4 billion years ago?
It's not entirely known, but based on dating of the surface, and we date planetary surfaces by looking at how many impact craters are on them, which is not the most, elegant method, but it's what we use. And from that, it appears that it's rare to find these very large fluvial water-related geomorphic features later than about 3.8, 3.6 billion years ago. There are other examples of simple channels being carved near volcanic features and gullies that are present in the very near past, but these are very small, and they're usually related to some subterranean phenomenon, not something that was happening actively at the surface or in the atmosphere. They're not rain related, I guess is what I'm saying.
So how old is the planet itself?
Roughly the same age as the Earth, which is 4.56 billion years, give or take, based on radiometric dating of asteroids.
So the atmosphere didn't last very long.
No, it didn't. And this is largely due to the fact that it's small, so it didn't have a geodynamo to protect the atmosphere and less gravity to hug the atmosphere close.
Right. Doesn't that make the chances of actually finding even microbial life on Mars pretty slim? Because it had this very small window to show up and do things in?
Yeah, I mean, no one knows how long it takes for life to get started or form. So maybe it was plenty of time. There's evidence of life on Earth going roughly 3.9 billion years ago. So
there's evidence perhaps of water even before that. So life might start really quick. And then if it can adapt and perhaps, move to subterranean habitats, perhaps there's still life on Mars in these underground reservoirs that it's moved into now that the surface is no longer habitable.
There are some crazy ideas that because of Mars's smaller size, it would have cooled more quickly than Earth and thus been more conducive to life earlier than Earth would have been. And so life may have taken root on Mars before it did on Earth.
Well, we should probably send some robots over and check it out.
Yeah, we
Well,
do.
actually, one is on its way
throwing-
as we speak.
Is there right now?
Yeah, the Mars
about a week
laboratory.
ago, we shot one off.
So earlier you were talking about how there's a difference between how the lakes form on Titan as how they form on Earth.
Well, not a difference. We're just not sure how they form on Titan. And one idea is using the Earth actually as an analog. We do this all the time. We look at things on the Earth and we look at other planets and we say, hey, this thing looks a lot like this thing we see on Earth. So we're going to see if the same process happens on different planetary bodies. So one process that happens on the Earth is called karstic lake formation. So limestone is really soluble in water. So if you take a big limestone formation and water is able to percolate through it, it will dissolve and form big caves underground. And then these caves tend to collapse, forming big pits. And then water can fill in these pits to create karstic lakes. And so one idea is that perhaps the lakes we're seeing on Titan are formed through this process, because they look an awful lot like karstic lakes on Earth. But the question is, how is this happening on Titan? Because water ice does not seem to be soluble in ethane or methane. So you have to be dissolving something else. So perhaps Titan has this huge layer of organic crud on the surface that is soluble in methane or ethane. So maybe that's why we're seeing these features that look like karstic lakes on the Earth. So it's not limestone and water, but maybe it's solid acetylene and methane that are forming karstic lakes on Titan. Same process, just different materials.
Crazy.
I know.
So at this point in time, yeah. So are there any other questions or topics you guys want to cover?
Did you want to touch Lorenz's maximum entropy production? One of my favorite planetary scientists is this guy named Ralph Lorenz. He produces very bold ideas and that are very interesting. They may be right, they may be wrong, but at any rate, they're incredibly interesting. And so he wrote this paper. I forget the exact title, but it's something like Maximum Entropy Production on Earth, Mars, and Titan. And so he looked at the temperature gradients as a function of latitude. So what's the temperature at the equator? What's the temperature halfway to the North Pole? And what's the temperature at the North Pole of these three bodies? And then looked at these gradients as if the atmosphere was an engine. So an engine operates with a cold temperature reservoir and a hot temperature reservoir. And then it does work by moving material from hot to cold.
Right.
And the efficiency of the engine is based on the temperature of these reservoirs, and the amount of work produced is also based on the amount of material moved and the temperatures. And another way of looking at work is how much entropy is produced, because when energy changes hands, entropy is produced if it's a non-reversible process, which atmospheric heat redistribution is. And so he looked at these three different bodies and then noticed that there is a fairly large temperature gradient between the equator and the pole, such that the amount of entropy produced is maximized. So if there was no temperature gradient, then the entropy would be zero. And if there was a temperature gradient such that it perfectly matched the re-radiation back to outer space, a temperature gradient that matched the radiation it was receiving from the sun, then there would be no heat transfer. And so then the entropy production would be zero. But on all three of these bodies, it's somewhere in between such that it maximizes entropy production. And so using this entropy production model, he was able to predict the behavior of these three atmospheres and match it with the actual temperature gradients that we see on these three different atmospheres. So it's this cute, clever idea that is definitely on the cusp of, thermodynamics, sort of, but I found it quite intriguing.
So this model has a predictive element to it that could be used on other planets if we had an idea of what their temperatures were like at the poles and the equator.
Right.
Interesting. But we don't have anything that fine enough a measurement to measure that, generally speaking, on other planets. Right?
I don't think we do yet. It may be coming with Kepler. I'm not sure. But it's a new idea, this maximum entropy production theory. And some people accuse it of being a pseudoscience because it's difficult to test.
Right.
And it's difficult to
like
find.
dinosaurs on Titan.
Yeah, I wouldn't damn it that far, but people can start to make bold claims with maximum entropy production, like it can govern the evolution of the entire universe. But whether that's testable or not remains to be seen. It's a relatively new idea. It came out of information theory during the 70s. Schrodinger even talked about it when he tried to define life back in the 40s, and he said that life feeds on negative entropy. It's an open system that feeds on negative entropy, but it hasn't been entirely accepted, and I don't know why. I'm smart enough to find it very attractive, but not smart enough to know why people are scared of it.
Okay, we covered everything.
Hooray!
Time to do the wrap up. Okay, so thank you, Charlie. Thank you, Catherine. You have pleased me. Your efforts have borne fruit, and that fruit is sweet. So, to thank him for his efforts, Charlie gets a rambutan. Good. Enjoy that rambutan. And
I popped it into my mouth.
Catherine gets a durian.
Ew.
Oh, no, she doesn't like it. Okay. So I'd like to thank my guest, Ryan North. Thank you for coming on.
My pleasure.
Yeah, this was really good. You asked great questions, and now we know more about Titan and lakes.
And the dinosaurs that live underneath them.
And the dinosaurs that
I mean, according to Dr. Catherine.
That's right. According to Dr. Catherine. So you can email us at barn@titaniumphysics.com, or you can follow us on Twitter at @titaniumphysics. You can visit our website at www.titaniumphysics.com, or look for us on Facebook. If you have a question you'd like my titanium physicist to address, email your questions to tiphyter@titaniumphysics.com. That's TIE Fighter at Titanium Physics. And if you are a physicist and would like to become one of my titanium physicists, email physics@titaniumphysics.com. We're always recruiting. The Titanium Physicist podcast is a member of Braculope Media. If you've enjoyed the show, you might also enjoy Science Sort of or The Weekly Wienersmith. Check them out. The intro music is by Ted Leo and the Pharmacists, and the end music is by John Vanderslice. Good day, my friends, and remember to keep science in your hearts.
Angela, don't be mad. There's something I gotta tell you, dear, before you come back here. I lost your bunny. I let him out of the cage. He was eating spring mix on the carpet, jumped through a window out into the haze, hop down Magnolia Boulevard, no way he'll survive.
Well, we should probably send some robots over and check it out.
Yeah, we
Well,
do.
actually, one is on its way
throwing-
as we speak.
Is there right now?
Yeah, the Mars
about a week
laboratory.
ago, we shot one off.
Man, I love that you guys can say "we" for this. I don't get to do that.
Not that I was involved at all. So.
No.
I
You have
wasn't-
this
I wasn't
scientist
involved
bug.
either. I very liberally used the term "we."
Well,
Yeah.
I think I'd like to say that I helped dissuade them from choosing one landing spot, but that's all I did.
That's pretty good.
cool.
Yeah. How'd you do that?
I did this redistribution of subsurface materials due to impacts calculation. To say that maybe the clays, these hydrated minerals we see in one location might not have actually formed on the surface. They may have formed underground, and then a big impact crater just dug them up like a steam shovel and threw them on top of the ground.
Sounds plausible to me.
Yeah. I guess it's not the most exciting thing, but I thought it was cool.
So where is it going now, Charlie? Which
It's going
site did they decide on?
It's going to a very safe site on the equator, which is Gale Crater. It's still an interesting place because there are gullies on the side of Gale's walls. There's a small valley network, and there's an alluvial fan. An alluvial fan is something that forms from a stream that's carrying material downslope over a long period of time,
Right.
such that it deposits material, and then the stream becomes rerouted because there's this pile of material now. And so then it will deposit material somewhere else, and then it sweeps back and forth trying to find the place where it's deposited the least amount of material until after many iterations of this, a large fan-shaped structure develops. Right. And so these are sexy for planetary geomorphologists because that means that stream was flowing for a prolonged period of time. So it's going to land on that thing and drive around.
When does this happen?
I don't know. How long does it take to get to Mars? About 6 months?
About 6 months. So next summer.
Well, something to look forward to.
Yeah. Hey, well, if it lands, cross your fingers safely.
Yeah, it's got this crazy landing scheme.
Yeah.
What's the landing scheme?
It has first it enters the atmosphere with a big heat shield and does this behavior called aerobraking, where the heat shield just slams into the air and that slows it down. And then once that gets hot enough, and then once it's descended to enough altitude, that heat shield will pop off, and then it'll light like 4 jetpacks on all sides of it, and then the jetpacks will continue to slow its descent, and then the jetpacks will continue to burn as there's like cables that begin to lower the sky crane cables. 4 cables start to lower the rover, and then it softly drops the rover onto the surface of Mars, and then the jetpack carries the sky crane off, and it crashes somewhere.
Yeah. You need to Google this. It is the craziest video I've ever seen of a spacecraft landing on the surface of Mars. But then again, we threw airbags at the surface of Mars, 7 years ago, and that worked like gangbusters. So who knows?
It's just there's this engineering concept that the failure rate goes with the square of moving parts. And there are a lot of moving parts to this scheme.
It's got 4 jetpacks involved, which seems like, there's a possibility.
And 4 cables, too.
Yeah, but there's also a possibility for awesome stuff.
Oh, yeah. No. Of course. So keep your fingers crossed.
Why don't we have jetpacks here? Why can't I buy a jetpack?
You can buy those water jetpacks. I was looking at this gift site for millionaires the other night, and they have this, you put it in the water and it sends a stream of water into your backpack that shoots out in jets, and you get to hover above the water with your water jetpack. They also
had, do you have a lot of millionaires on your Christmas list? No,
I just, if I had some, maybe they'd want to buy for me, and I could give them ideas. They also had a water ski. People like water skiing, but need someone to go in the boat for you. This is like a little Sea-Doo that you control from the handlebar on the water ski behind. And so it's a 1-person water ski mobile.
Oh, wow. That's lonely. That's cool.
Yeah, you don't need friends when you got that. And maybe this can be adapted, bring it back on subject to, landing on Mars somehow.
Or water skiing on Titan's lakes, Like I said, next beach resort.
But we would die instantly, even if we had...
You would not die instantly. It would take several minutes to suffocate.
So on Titan, you wouldn't want to wax your skis, right? Because the wax would stick to the hydrocarbons. What would you do?
Oh, yeah. Let's see. That's a good question. Because they're mostly non-polar. So I don't know if it would even matter. I'm not sure if you could do anything. I'd have to think about that.
Maybe there's a paper.
What's slippery on gasoline? I'll have to figure that out.
Banana peels?